Hello everyone, this is Dr. Lennon, and in this section, Unit 5A, we begin our study of statistical reasoning. So in this section, there's a lot of just basic definitions and examples that, you kind of say, well, is it this or is it that? So we'll be looking into things, just some basic definitions, and then the majority of it is going to be distinguishing between whether something's an experiment or an observational study. So statistics basically collecting, organizing, interpreting data. There's a lot of tools to do that, and there's a lot of different things that you can use to talk about the middle of the data, the range of the data, the variance of the data, stuff like that. And we'll spend time in the future looking at lots of different ways of doing that. So the statistics are actually the data that describe or summarize something. So the population in a study is the complete set of people being studied. So the only time you would actually ever study all of them is if you're doing what's called census data. Typically what we do is we try to look at a sample and use that to extrapolate things about the general population. And there's lots of different ways to sample. We generally want to be involved in random sampling, so we're not including any of our biases or having them come from things like self-reporting, sampling, stuff like that, because a lot of times people will have certain incentives to want to involve themselves in a study, and that can corrupt your data or influence your data, I should say. So the sample is the subset of the population where we actually obtain data. Parameters are numbers describing the characteristics of the population. And sample statistics are the numbers describing found by actually looking at the data collected by the sample. So those are basic definitions, and we'll look at some examples. Okay, so we want to describe population, sample, population parameters, and sample statistics. So in this scenario, we have agriculture inspectors for Jefferson County measuring the levels of residue from 3 common pesticides on 25 ears of corn from each of the 104 corn-producing farms in the county. So your population, you're trying to learn about all the corn in the county, all the ears of corn in this Jefferson County. The sample is the 25 ears of corn that we actually measure it from. And then the population parameters are the pesticides that the levels of residue from the pesticides. And then the sample statistics are the actual residue from the pesticides you collect on the 25 ears of corn that you have. So pretty straightforward. So population, all ears of corn in the county, that's what we're trying to learn about. Okay, so the sample is the 25 ears of corn that we talked about, and the parameters are the average levels of residue, and then the sample statistics describe the levels of residue on the ones we actually measure. Pretty straightforward. So in a study, what are we trying to do? State the goal of our study. Choose a sample. Again, there's many different ways of sampling, and we'll talk about that in a moment. We'll look at those examples. Collect the data, and then look at your sample statistics, and then use the sample statistics to infer the population parameters. And there's varieties of ways of doing statistical testing that we'll look at. There's confidence intervals that we'll look at the end of the day, and then there's also hypothesis testing. Those are 2 of the common ways that we'll look at using our sample statistics to try and infer things about the population. And then, you draw your conclusions. Okay, so here's a flow chart that kind of describes it. Start, figure out your population, take a sample, look at your sample statistics, make inferences about the populations, and then say what you concluded. Not all of these experiments necessarily give you something, like any type of scientific type of inquiry. Sometimes you run an experiment and you might have an intuition about what might happen, but sometimes, there's not a strong conclusion that can be drawn, and that's okay. You may just have to look at something else or a different characteristic, or run another experiment. Okay, so let's look at this. Each month, the U.S. Labor Department surveys 60,000 households to determine the characteristics of the U.S. workforce. One population parameter of interest is the unemployment rate, the percentage of people who are unemployed among those who are either employed or actively seeking employment. So describe how the 5 basic steps of statistical study applied to this research. So this is basically telling you how to draw a statistical study here. So step 1, we want to learn about the employment, the population who are either employed or actively seeking employment. So the Labor Department chooses a sample, in this case 60,000 households. Again, kind of depending upon the tools you have to work with and how easy it is to collect data, often will determine how many people that you can sample, or how many things. It doesn't have to necessarily be people. In this case, it is. And then they ask questions in the sample. The responses constitute the data. And then we look at sample statistics, such as percentage of people who are unemployed. Based on the sample statistics, they make estimates for the population parameters. And, so they're inferring about the unemployment rate for the entire United States based on those sample statistics they got from the 60,000 households that they investigated. So then they draw conclusions. They might use current and past unemployment rates to draw about whether jobs have been created or lost. So you hear about this sort of thing on the news all the time. This is definitely a very common type of statistical analysis that's going to go on in the Labor Department. All right. A representative sample is a sample in which the relative characteristics of the sample of the members are generally the same as those across the population. So just an example why something like this is important. Say you were trying to find the average male height in the United States. If you took a sample of individuals and say they all were a part of the NBA, that's not going to be a representative sample, because typically people in that population have very well above average height. So you want to use some sort of random sampling so that you don't have a lurking variable influencing or creating some sort of bias for your statistical analysis. So simple random sampling is something you want to have, a sample of items such that any person in the population has an equal chance of being selected. So that's important. That's an important notion. And there's different ways to do that. So systematic sampling is one way, you just do it in a systematic way. So selecting every 10th or 50th member of the population. Sometimes that can be effective based on what we're looking at. If you're looking at every household, though, that's probably not going to be the most effective method because the list would be so long. Convenience sampling, such as people who happen to be in the same classroom. This sometimes is not the best method. It's often the easiest, but many times it's not going to be a truly random sample because, if you selected people that were in the same classroom, if people that went to college versus people not going to college influence the data, it would be a bad method because, you wouldn't be, people that didn't go to college wouldn't have an equal chance of being selected. Okay, stratified sampling. First, before you do your simple random sampling, you divide the population into distinct subgroups, and then you take a simple random sample from each. So it's called stratified because strat is a synonym for subgroup. Okay. Okay, so sampling techniques. Simple random sampling. Every sample of the same size has an equal chance of being selected. Computers are often used to do this using some sort of pseudo-random algorithm. Convenience, systematic, and stratified. So those are the main ones. Again, using randomization analysis by computers is a very, very common one. Watch out for convenience sampling and stratified sampling. You have to be careful to make sure that you're drawing from the groups in and not making mistakes in that way, creating some sort of lurking variables. Okay, so we're going to identify the types of sampling that occur here. one of those 4 topics. So you're conducting a survey of students in a dormitory. You choose your sample by knocking on the door of every 10th room. Now, so that sounds very systematic on every 10th room. It's also, it's kind of a combination because inside your dormitory, that's also a kind of a convenient way of sampling. So you could make an argument that this is a combination of convenient sampling and systematic sampling. Probably they'll just say systematic. Let's see. Yeah. Systematic. All right. To survey opinions on a proposed new water line, a research firm randomly draws the addresses of 150 homeowners from a public list of all homeowners. So, that's just a simple random sample, right? Because we're randomly drawing it. We don't know how they're randomizing it, but, most likely just a computer algorithm. So yeah, simple random sample. All right, so agriculture inspectors check the levels of residue, one of the ones we looked at earlier, on 25 years of corn from each of the 104 corn producing farms in the county. So kind of they're grouping them here. So that should be an example of stratified sampling. Yeah. So they are using stratified sampling based on each of the farms. So those are the groups. Anthropologists determine average brain size by studying skulls found at 3 sites in Southern Europe. Again, that's just convenient because probably those are the ones that are available to them. Yeah, little choice, so it's a convenient sample. All right. However, it seems reasonable to assume that these skulls are representative of the larger population. Yeah, perhaps. But, probably if you're near that field, you would know that. Typically, if you were just a statistician, you might not know something like that. So, probably that is a factor. Okay, bias. So we talked about this earlier, and we gave some examples of biases that might arise with like the height example and things like that. And those are what you always have to watch out for because it can really ruin a statistical study. So a statistical study suffers from bias if its design or conduct favors certain results. Observational study observe or measure characteristics, but do not attempt to influence or modify these characteristics. So this is different from an experiment because in an experiment you're offering a treatment and you're studying it against a control group, someone that doesn't have a treatment. So that's the main distinction here. So you're just observing things, but you're not actually trying to modify the characteristics. In an experiment, they apply a treatment and they observe the effects. So there's also a control group that doesn't receive the treatment, and that's who you compare it to. So the treatment group is the sample members who receive the treatment, and the control group is the members that do not receive the treatment. And again, it's still important to randomly select them and be alike in all respects except for the treatment. So a placebo, when you run an experiment, the people that are receiving the treatment often don't know whether they're in the control group or the treatment group. And so often just the idea of receiving something that they think is a treatment, can mentally influence someone into thinking they're getting well. And so that is the placebo effect. So this refers to a situation in which patients improve because they believe they're receiving a treatment, even if they are not. So blinding is basically who knows when the experiment is going on. So a single blind experiment happens when the patients do not know whether they're in the control group or the treatment group. A double blind experiment happens when the experimenters, the people receiving the data, don't know who's in the control group or the sample group as well. So single blind, the participants don't know whether they're a control group or treatment group, but the experimenters do. Double blind, neither the participants nor the experimenters know whether they're in the treatment group or the control group. So let's look and see what's wrong with each of these experiments that are set up. So example A chiropractor performs adjustments on 25 patients with back pain. Afterward, 18 of the patients say they feel better. he concludes that the adjustments are effective. Well, the problem with this is every single person received the treatment, so there's no control group to compare it with. He should also have a group of 25 patients, and they don't do that if you were actually running the experiment, and then you could compare their improvement over time. Yeah. So, yeah. So let's see what they say. 25 patients are a treatment group, but it lacks a control group. The patients may be feeling better because of a placebo effect rather than a real effect. The chiropractor may have improved a study by hiring an actor to do a fake adjustment, one that feels like a real manipulation but doesn't actually conform to chiropractic guidelines on a control group. And you could have compared the results of the two groups to see whether a placebo effect was involved. Okay, example B. A drug for a new type of attention deficit disorder is supposed to make the children less disruptive. Randomly selected children suffering from the disorder are divided into treatment and control groups. Those in the control group receive a placebo that looks like the real drug. The experiment is single blind. Experimenters interview the children one-on-one to decide whether they become more polite. Well, this one's a little bit tricky. There's nothing really wrong with like how they ran the experiment, but the way they collected the data isn't a good idea. This should be a double-blind experiment because since the experimenters know and they're collecting data based on interviewing the children, that may allow how they report the data to have some biases there. So really the people interviewing the children should also know not who's in the treatment group or control group. So that's basically what it says here. During the interviews, they may inadvertently speak differently or interpret behavior with those children because they know what's going on. So a double-blind experiment would have been better here. Okay, retrospective study. So sometimes, there's reasons that we can't run a real experiment, for ethical purposes or just historic reasons. So a retrospective study is an observational study that uses data from the past and divides a group of cases engaged in the behavior under study in a group of controls who did not. So basically you're looking at people that did something in the past versus people that didn't and seeing if there was any difference in what was going on there. So for which type of study is it? For each of the following questions, what type of statistical study is most likely to lead to an answer? So what is the average income of stockbrokers? Again, so you could do a retrospective study here. So an observational study tells us the income of stockbrokers. You need to only observe the brokers. Okay, so you actually don't need a retrospective study, but I was thinking that you could do one here. A retrospective study is a type of observational study, but I guess you could do a current one as well. So there's no need for that to necessarily be retrospective. Do seatbelts save lives? Okay, so this one you would want to do a retrospective study because ethically, if you try to observe people, well, first of all, there's seatbelt laws now when there didn't used to be. And also, so it would be illegal. But secondly, it would also be unethical because, if it turns out that seatbelts are a valid safety precaution, you'd be putting people at risk. So retrospective would make sense here. Again, it's unethical to tell some people to wear seatbelts and not to wear them. So you would want to conduct a retrospective study. And turns out that, in a study, you could compare death rates, and it learns that seatbelts do save lives. Can lifting weights improve a runner's time in a 10-kilometer race? Well, here you can just run a regular experiment, right? You could put some runners on a weight program and have other runners just do their typical training and look at the results after a manner of time. So, you'd run an experiment, look at the 10K times, put some on a weightlifting program and other ones not, and then look at the differences in times. Look at their improvement and see which if one group improved more drastically than the others. All right, there's an interesting note at the end. We can't use blinding in this experiment because there's no way to prevent participants from knowing whether or not they're lifting weights. That's kind of funny. A new herbal remedy to reduce the severity of colds. Again, you could run an experiment here. You could have one group take a water pill and another one take the herbal remedy in pill form, and over the course of time, see who reportedly got sick from the common cold more often. So, and you could do a double-blind experiment. So the experiment that I described could be double-blind. So because you would be giving both patients a pill that looked the same, the patients would be blind, and then you could have people collect the data that weren't aware of who took which pill, or if it had to be done in interview form. So, yeah. So you could do that as well. All right, margin of error. So this is confidence interval. This kind of stuff will come up a little more in the future. Basically, when we run, we'll do experiments when we can run confidence intervals to, look at the chance that a true value of a population parameter lies in an interval, or a confidence that a parameter lies within an interval. And we'll talk about how to do that later. It kind of depends on some factors. But the margin of error is basically the distance from the middle to each side. So we'll look more at this in a minute, but let's look at so you've got your sample statistic minus your margin of error. That'll give your lower bound, and your sample statistic plus your margin of error will give your upper bound. So an election poll finds 52% of surveyed voters plan to vote for Smith, and she needs a majority, more than 50% to win a runoff. Margin of error in the poll is 3 percentage points. Will she win? Well, if it's 52% of voters, the lower bound would be 49%, 52 minus 3, and the upper bound would be 52% plus 3, which is 55%. So because 49% is within the bound, there is a chance that she will not win. So you can't say for certain. But yeah, so they say they can be 95% confident here. You would actually need to know the standard deviation to be able to say that for sure, and that the population is normally distributed. But we'll talk about that in the future. Anyway, that's it for this first section. So basically looking at observational study versus experiment and different ways to sample data. So that's it.